Professor Frank Armstrong, Ferris State University. This is our third video now for our Management 370 Quality Operations course. And in your book, on problem number 11, you'll see that there is a chart of January through December. And what this is a measurement of the crime rates and crime complaints during a 12-month period to see if they have a controlled process, if you will. And you can do this with service industry or defective parts, whatever. But in this particular case on number 11, in January, they had 7 reported crime incidents. Each sample size was of 1,000. So out of 1,000, let's say, police calls, 7 of them were crime incidents. So to figure the mean, you take and divide 7 by 1,000, which gives you 0.007. And you look at the chart, all the numbers are there for you. February, there were 9. So again, 1,000 each month. So the mean for that was 0.009, and so on each month right until the December. If you add up all the incidents, the number is 100. If you add up the size, we have 1,000 each month. The total population is 12,000 caseload. And then you'll figure out your average crime rate number. So now let's take a look at our numbers and calculations so we can make some sense to this for you. All right, the formula for P-bar would be the total defects, which we added up over there, comes to 100, divided by the total samples. We had 12 lots of 1,000. So total samples was 12. The size per sample was 1,000. So you take that, multiply it by that, divide it into that, and your answer is 0.008333. Okay, so now we have that number. That's our P-bar. Then we got to figure out our standard sample deviation, or our sample standard deviation. And that formula is SP, and that's the indicator for a P-bar standard deviation. You take P-bar, which now we know is that number, times the number 1 minus P-bar. You divide that by the size of the sample. So in this case, we have 1,000 samples. So our formula is 0.008333 times 1 minus 0.00833 divided by the sample size of 1 lot, which is 1,000. So our answer is, the standard deviation is 0.00287. So that means between the 12 different samples, or 12 different months of sample sizes, the average deviation between the average number of each month is 0.00287. All right, now we got to figure our control limits. This formula is very simple. We have an upper control limit, which is P-bar, again, 0.08333, plus 1.96 times the standard deviation. Well, Frank, why 1.96? 1.96 is the number that you use for a 95% confidence level. So that would be your confidence level. If you use a 90% confidence level, this number would go down. If you went to a 99, that number would go up, and so on. Typically, when you do statistics, 95% confidence level. That means you're 95% sure these numbers are pretty accurate. You always give yourself a 5%, it could have been wrong. So, using those numbers, P-bar plus 1.96 times our standard deviation gives us a number of 0.01396. So in our P-bar, our upper control limit is going to be 0.01396. Or if you want to round it off, 0.14. All right. Our lower control limit, much like you saw with the other formulas for control limit, is now a minus. P-bar minus 1.96 times SP, because that's the lower area that you want. And again, 0.00833 minus 1.96 times 0.00287, and you get a 0.0027. So the lower control limit is 0.0027. And that means every plot needs to be inside of there. And then we can say that we have a process in control. And again, you can do that with any service item. You can take and measure the hospital or clinic, number of correct bills, how many mistakes were there in the billing that caused delays. You can measure the defects in parts that you manufacture, typically in a size of 1,000. We could say we had 7 defects, we had 9 defects, and so on out of 1,000. And you would have a P chart. That gives you an understanding of how your process is in control without actually dealing with the measurement size. You're looking at defects or errors, okay? Okay, again, now we're going to go and look at the chart. How do you plot a P chart? We already know what our center spec is, and that would be 0.008333. That was our P bar, so that's our center line. And if you look at the numbers there, you'll see that just above 0.008 on the left-hand side, going across, is where we plant the center line. That means if everything was perfect, we'd be hitting that line every time. Unfortunately, nothing is perfect. I don't care how many parts you manufacture, you'll never make perfect parts. So you're always going to have a variance, and that's normal. Okay, now, we plotted our upper control limit up there at 0.014 because we rounded off 0.1396. And the lower control limit, we kind of left right around 0.0027 here. Upper control limit is a little bit bigger number, so you could round it off to 0.003 if you wanted to. But anyway, you plot then the mean. So remember, our first month, January, had a mean of 0.007. February had a mean of 0.009. The next 3 months were at 0.007 again, or 7 incidents per 1,000. So you plot your chart that way so that you can look at it and go, okay, we are within our normal operating range. If you had some that were up above the dashed line or below the dotted line, you could say, wow, we're less than normal, or up above the line, we have more than normal frequency of crime incidents. So you can see what your norm is and what your current trend is. Here, if you look at the tail end, it looks like the crime rate is going up just a little bit, and that's typical right around November, December, go up. And then right after December, it kind of tapers off again, probably goes back down to normal. So this way, a police department could look and say, well, you know what, we're operating in kind of a normal range of crime for our area. Okay, I hope that answers the questions. Again, I will post this chart and the other figures right along in a document with this video so that you can look at the both and hopefully get it.